So that's the problem. So far it's all Sinai. And here comes an idea which maybe is not Sinai. We have a formula for diffusion constant. It says start every place in the space, go time t, and see how far you got on average, what your square deviation is, and the claim is that it's second derivative of something. Now what is this derivative? Because we have the space which is covered with identical copies of elementary cell, it's good enough to average over one copy of elementary cell. So I'm allowed, even though I'm studying infinite diffusion or infinite space, I'm allowed to start in a little compact domain. So this integral here is all initial points in here in the space. I'm allowed to stay in the space because I know that every trajectory in the space has its sister in a large space. So this part is all happening on the compact domain, but here I allow myself to put a weight which says how far I went in a big space. So this is going to produce my weights. So this is the idea. If you agree with me on this thing, then we know how to do the calculation. This will turn out to be an integer. It'll be an element of discrete translation group. Because what happens is it'll have a support on periodic motions, on relative periodic motions, which close once I quotient the group, and group is discrete. So this will actually be integers. It'll tell me how far I go in one repeat of this periodic orbit in a little space. In a big space, it goes there. The big space stays. And that number will be 0 if I don't leave, if I'm periodic. And it'll be non-zero if I'm relative periodic, or I'm periodic up to a translation. So that's the idea. Now, all the machinery that I developed now just works. And the machinery that I explained was that the way to compute averages, I had to compute derivative with respect to beta that produced these cycle formulas. So on every periodic orbit, the second derivative produced the weight like this. The mean time was divided by time, and these are the cycle formulas, periodic orbit formulas, and these are exact formulas. We have exact formula. The only problem is how convergent is it as I add more and more periodic orbit. But it's exact because it has minus signs. It's nicely convergent because it's designed to be exponential or super exponential convergent. This is the real time. Then again, if you read this cheap book on the internet, it tells you that discrete time and real time, you only have to compute it once. They're very related in very simple ways. So that's section in the book. So it doesn't matter whether it's a real or integer time, but here I'm using real time because that's what you care. You have a diffusion in time. But it turns out if you do it in integer time, there is just one conversion factor, which you compute only once for all averages. So that's it. So then, unfortunate graduate student is stuck onto this, and it turns out it's kind of hard to do. But it's be easier for Tingang because we are smarter, a little bit smarter now. So very good student. He starts working, and he starts finding periodic orbits, and their number grows rather quickly, but it's doable. It's not so hard once. It's like 3-disk problem, a little bit harder. It's not much harder. Then there is something in literature, which is statistical mechanics. So they're totally off the wall. So their number is really bad. That's the best statistical mechanics estimate. Then there is numerical calculation, which in this case is reasonably good. And computation using periodic orbit theory is good to a few percent. Usually it's much better. So, it agrees with numerical computation, but it's not very impressive. And we know why. One reason is that there's lots of pruning, and that makes it very difficult for these things convergent. Second one is that we are stupid. We didn't know how to quotient the discrete symmetry. And I told you if you don't do that, you will pay the price. So we are paying the price here. that's that. So now you think about it, say, okay, let me understand this in more detail in one dimension. So on next lecture, I'll do something you can do by hand. And you learn a lot. You learn a lot by thinking.